Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is a very interesting MCQ and the question is in front of you. I request everyone please pause the video, try by yourself, and whatever answer you get please write in the comment box along with few words as explanation. I believe we have tried, so let's start. Now the question, which energy diagram best represent this given reaction or conversion? I mean this transalkene into cis-alkene. Okay, and 4 energy profile diagrams provided, which one is correct? Before going to the details, let's learn how this conversion takes place. If you look at these two methyl groups, they are 180 anti to each other, whereas in case of cis their angle between angle is 0 degree. Now generally CC rotation in pi bond is actually restricted. Why? Because of in-phase overlap of these two p orbitals. Actually they happen by parallel or sidewise overlap. For example, if you consider this is your x-axis, this is your x-axis, and this is y-axis. Now this one is obviously px, it is also px. This px can undergo parallel or sidewise overlap. By chance, if you want to rotate this cc, then obviously it will go to py, means this x right now will go to py. Now if you look at this px and py, they are not parallel to each other. That's why the sidewise overlap will not be possible, although 2p orbital each will carry single electron. So if you look at here and here, there are 2p orbitals each carrying single electron, means you may consider that this is actually diradical. Now this diradical have two options. One, it can go back to its reactant, or it can go back to this cis one, I mean product. Here one intermediate possible, and that could be go back to the product or reactant depending on its situation. Now so since here one intermediate, so you can say, sir, this is your step 1, this is your step 2, so 2 steps possible. Now if you understand this much, so from there you can cancel option A and option C. Why? Because if you look at, this is your reactant, this is your product, this is transition state, only one, no intermediate. But during our discussion I have told there should be one intermediate. Now if you look at trans is actually more stable compared to cis. That's why you may say, sir, this is trans, is more stable. So if you look at, this is your reactant, this is comparatively lesser stable than product. No, this is not. So obviously option D is the right answer. Here transalkene is more stable compared to the cis one. By the way, please do not say cis is unstable, trans is stable. No, there is a difference between less stable versus unstable. I would say this is lesser stable compared to trans, but not unstable. Please be careful. And this is the position of intermediate. By the way, since it's a 2 step, so there is a transition state 1 and transition state 2. Another thing, student, the intermediate diradical is significantly reactive enough. That's why the second place, the energy of activation for this diradical to the product, I mean the cis one, is relatively lesser. So reaction can happen very smoothly. But here these overall conversions of energy of activation will be significantly higher as the reactant is comparatively more stable. So this is significantly higher, student. Okay, so if you get this question in your exam or less than 30 seconds, how could you solve? You need to remember this is a 2-step process, so option A and C gone. Another thing, you can clearly see that the reactant is more stable, so this is the right answer. Very easy. Now in conclusion, what you have learned, that sigma bond can rotate freely due to head-on overlap, but pi bond cannot rotate due to parallel or sidewise overlap. And by chance, if you want to rotate the pi bond, the overlap will go and the bond will break and it will result a diradical intermediate. Next point, since the intermediate is not stable enough because radicals are 7 electron species, incomplete octet. That's why the corresponding energy of activation for this CC pi bond rotation is expected to be higher. And the last point, transalkene is more stable than cis counterpart due to sterically and electronically. What do I mean? These two methyl groups are far away. Here they are closer, so steric repulsion works. Not only that, if you look at the dipole moment in case of trans is 0, whereas in cis case, I believe it's a very small value, but still it exists. So from that perspective, you can say that, okay, sir, electronically, trans is also more stable. So this is the overall discussion. Thanks for watching. See you in my next video. Bye-bye.